Great, let's get started. I've got a lot to talk about and not a lot of time to do it in, so thank you for coming to hear about the state of the project for Swift. By way of introduction, my name is John Dickinson. I am the PTL for Swift. You can find me online in various places under the nickname Not My Name. First off is a very high-level intro. Swift is an object storage system, and the whole point of that is not to provision storage capacity or something like that. The whole point is to abstract away the storage media from the data that's stored on top of it. And the really cool thing about that is it means that your storage media can come and go, you can add new stuff, you can upgrade, you can use whatever the latest gen stuff is, all without worrying about how that impacts your data. And so what you get from Swift is a durable store that's massively scalable, extremely highly available, and can handle a huge amount of concurrent throughput. And so that's the point. It's fantastic for storing unstructured data, pictures, videos, backups, internet content, whatever you need. And it's being used to do that all over the world every day, which is awesome. So speaking of all over the world, let's get into some of the exciting things that have happened, and then some of the things that people are talking about, and then I'll talk a little bit about the state of the community itself. So one of the things that just happened is in the last release, we completed the global erasure code feature. So we've had replicas originally, then we added in the ability to use erasure codes for that. If you're not familiar with what erasure codes are, it's a way to split up the original data into a relatively large number of individual pieces such that you can lose a subset of them and still get back the original data. And you can do this without the overhead that a full replica would take. So where a 3x replica would take 300%, you need to store 1 gigabyte, you have to save 3 gigabytes to do that. With erasure codes, it's reasonable to even get into like a 1.5 overhead. So, but you still get the same durability that you had with the 3 replicas. So it's a pretty cool thing. But because you're doing more individual pieces and you've got more coordination going on inside the cluster, which means that in a lot of cases, erasure codes don't really work well with globally distributed clusters, which is something Swift has supported for quite a while. So you can have an endpoint on Sydney and in Perth and in America and in Amsterdam, and you're good. You can store the data in a single namespace across that. But then when you try to add erasure codes, since there's a huge amount more of network communication that's happening to talk to all the individual components, you're more susceptible to a large number of timeouts, you're more susceptible to just nuances in the talking over the WAN and having to transport more data over that. That made it not good. But we fixed that. It's great. So you can totally have globally distributed erasure codes inside of Swift today as of the last release, which is fantastic news. And the basic way that this works is that instead of trying to take my original object and split it up into the erasure code pieces, we call them fragments. So you have these fragments, and then distributing those fragments all over the world, what we do is we can create the fragments, and then we replicate those fragments. So in this case, you don't get quite as much efficiency as you would have. You can still get better than 3x, but you're able to also have a fully reconstructible set in multiple regions. And so you get high durability, you still get high availability, and there's a trade-off on the efficiency on what you're able to on being able to, on the storage space efficiency, so that you can still meet the metrics that you need to as far as how many, your capacity that you have to plan out for in different sites. So I'm really excited that we had that. It's not so much of just one feature that had to be coded up to do this. It was a whole bunch of things, including being able to manage replicating erasure code fragments and being able to optimize some things about how things talk to each other across the global cluster, being able to do stuff like that. So it was a really great feature. You can take advantage of it today. And that was the biggest feature that was completed inside of the last release. So now we can go look forward and say, what is the community working on now that you will be able to see in the future? The first one is called, it's called lots of things, but for this sake, I'm calling it deep containers. And deep containers are a way to more efficiently store a little bit of the metadata that we store inside of Swift. So the Swift API is made up of 3 components. You've got an account, you've got a container, and you've got an object. The account is very similar to like a bank account. It's not like a user account. It's like a bank account. It's where you put stuff. It's where you get stuff out of. You can limit access of who else can put stuff there, but it's just where you put stuff. Then inside of an account, you can create a container. And a container is just a little subdivision of your namespace that's inside of your account. And then you can put all your objects, all your data, all your cat pictures and videos inside of as an object inside of the container. And so the account and container, in addition to providing a little bit of organization on the overall namespace, allow you to give some access controls to subsets of things, and they collect a little bit of aggregated metadata. So each container, for example, has a list of all of the objects that are inside of it, and how many bytes total that is, and permissions on that. And then also each account has a list of each container that is inside of it. So that's kind of how the internal accounting that you can use for chargebacks and things like that work. But the problem is, with the containers especially, is where you see this first, if you have an enormous number of objects that you want to store and you put them all inside of one container, that list of objects gets really, really big. And when we're talking about big, we talk about things like billions of objects. So if you have a billion objects you want to put inside of a single container, you can run into some problems. And most of the problems that would affect the API have been resolved a while back, but the operators still have a big problem, because the storage for the containers to track that list is a small replicated database inside of the cluster that's stored like an object like everything else. So it takes advantage of all the durability and availability stuff. But what happens when that gets really big? What happens when that singular database file, it's a SQLite database, what happens when it gets bigger than the hard drive that you have available? What happens when you have 1 billion, 2 billion or more objects and you need more than 1 terabyte and you've only deployed 1 terabyte flash drives for this storage? You run into some major problems there. Kind of on an ongoing basis, since these are replicated around, we need to make sure that there are multiple copies that stay in sync with each other. And it's harder to keep big things in sync than it is to keep small things in sync. So those are the 2 operator problems that we're working on solving. And the way we're doing this is to use database sharding the same way you would with scaling out kind of bigger database systems. And, but it adds some challenges, because we can't break the API, because users can't know that this upgrade happened. And you also need to be able to keep it durable and available in a cluster that's running. You can't turn the cluster off and upgrade everything and then turn it back on. You have to be able to do this on a real-time basis as it's serving traffic. So that offers some significant challenges. And we're getting closer. We're working quite a bit on it. This is probably the top priority community thing that's being worked on right now. And I'm pretty optimistic about seeing it in the relatively near future. So it's pretty cool. It's been a long time coming, and I know that there are many deployers who are anxiously awaiting it. One other thing that's going on inside of the community, it requires a little bit of history. I'll have to go through this very quickly, is that a long time ago we had a limited amount of S3 compatibility inside of the project. For various historical reasons, we extracted that and put it into another code repo. And that code repo today is called Swift 3 and lives underneath the OpenStack namespace. And a lot of people use it to provide an S3 interface onto Swift. One of the things that we are doing right now is taking the S3 repo and reintegrating it into the Swift repo. And basically what this means is that anybody who gets Swift will automatically have an S3 API available without having to go through any extra steps. So that's a pretty big deal as far as lowering barriers to entry, just recognizing that as far as the broader industry goes and the larger ecosystem goes, there's a whole lot more clients that speak the S3 protocol than speak the Swift protocol. And so this is something that will help facilitate adoption. One thing we've talked about in the past at various summits and within development groups and stuff is, well, Swift is going to rewrite all or part or something in Golang instead of Python. And this is, there's a lot of detail here, but just a quick little status update on this. The simple problem that we're trying to solve is, it's not a simple problem, but the problem that we're trying to solve is how, as hard drives are getting bigger, as you're getting more and more hard drives inside of a single server, network speeds aren't particularly going up. The drive buses are not particularly getting any faster, but we're getting lots more cores, lots more drives, lots bigger drives. And so it's very difficult with the current architecture of our storage nodes to make very efficient use of all of the available hardware capacity right now. So if you have, for example, 80 hard drives, 80 10 terabyte hard drives in one server, and you just assume there's 100 IOPS on each, how do you get a total of 8,000 IOPS available or doing stuff all at once? And especially when you want to balance that over 16 cores and a limited amount of RAM or something. So our current architecture is not great on this with Python and Eventlet, having to do with its concurrency models and Python's multiprocessing and multi-threading state. And it's a lot better in Golang, and we're still working on that. There's progress that we have to make to, architecturally and design-wise that is independent of a language. So that we're working on those things so that we will be able to make these improvements in the future. So still something that we're working on long term. The next thing that we're working on, something else that's going on, is it's a collaborate. They're individual features, but they're kind of tied together in sort of a data movement, data management sort of idea. And a few things here. One is what we call policy migration. And policy migration is being able to say that I've got some data stored in a container via one storage policy, and I'd like to set it to a different storage policy. And so maybe it's all replicated and I'd like it to be all erasure coded. And so how do we get the cluster to do that on the cluster transparently to the user where data still stays available? That's one thing. The other thing is tiering, which is where you say, I've got data in here in this replicated policy, but in this container that is replicated, but say after 30 days, I would like it to be moved to a different container that is erasure coded. And then the third piece on this is something that is required for this functionality, which is symlinks. And just very similar to a file system symlink. It's an indirection object so that you can access one thing at one URL, but you're getting the content from someplace else. So those are three other things that are continually being worked on in the community right now that we should be seeing in the future. And most of this work is being led by NTT, and they're doing a great job on that. Another piece of work that OVH is currently working on is solving some problems with lots of small files. When I say lots of small files, I mean lots and lots and lots and lots and lots and lots of small files. Since files are stored inside of Swift in a file system, there is a degree of file system overhead that is required for each one of these. And we would like to remove that so that you don't run out of inodes on your hard drive or on your file system before you run out of disk space capacity, and you want to improve the overall performance of being able to read and write data. The idea here is let's use kind of some slab files. It's not a new idea, but it's a really good idea. Let's use the slab files and indexes inside of that and being able to kind of sort it out ourselves. And again, that's work that's ongoing. Now, a couple of other things I wanted to mention kind of in the wider community that affect the ecosystem but are not happening directly inside of the Swift repo. One of these is something called Proxy FS, which I have talked about at previous summits. And as a disclosure, my employer is the people writing this, so I mean, I'm not trying to do an ad here, but the Proxy FS is file system access to Swift. And this is more than just like a gateway or something like this. This is complete bimodal access via CIFS, NFS, or the Swift API, or S3 API if you're using that, to the same data at the same time. And that's the real kicker here, is that I upload all my data in via the Swift API, and then I've got to process it through a few things, but one of those things requires an NFS mount. And this is what you can use here. You can have the same data. It's not, here's your file system data, and here's your object data. It is, here's your data, how do you choose to access it? And the really great thing about this is just last week, actually, while I was on the plane here, the button was clicked to make this repository public. And so you can actually take a look at this today and try it out. It's still early. It's a work in progress. It definitely works, and it's got some pretty cool performance considering everything it's doing. But yeah, take a look at it and try it out. And it's something that, again, I think will be a huge boon to reducing barriers to adoption. One of the other things, similarly, also recently made open source, is being able to synchronize data inside of Swift to, say, S3 or other Swift clusters, and potentially adding on Google Cloud, Azure, maybe even some more traditional storage vendors things. And the idea here is that I may have my on-prem storage with Swift, but I also need to take advantage of some capacity that is someplace else. And wouldn't it be great, though, if I can continue to access the data through the same endpoint? So, for example, I would say that I need to, when I put stuff inside of my Swift cluster, I can still access it via my Swift proxy servers, my normal endpoint as normal, but I can make sure that this data is also mirrored into an S3 bucket. And anything, yeah, so it just keeps it up to date. And then, let's say you're running some jobs inside of EC2. You can access it through the same endpoint, and it'll fetch it from S3 before it fetches it from the Swift thing, which may be a more expensive network hop for you to get. So that's kind of cool. Again, ecosystem work. This is also available. Both Cloud Sync and Proxy FS are available on the SwiftStack GitHub page. I was asking the whole community, like, what are some other things that are going on? And these are a couple of things that came up. As far as who is involved in the community, there's a lot of people involved in the community. We're probably, my last count is we were something at 714 total contributors to Swift. And these people are the primary day-to-day active, week-to-week active people. So I definitely thank you for all of your work and all your contributions in here. It's a pleasure to work with you. Are there any questions? I kind of blazed through that pretty quickly. We've got just a couple of minutes left. Bruno.
When you're uploading a large object to Swift, you have the option to split and do that in parallel. When you're downloading a large object from Swift, is there anything that will do the same for you?
So the question is, when you're uploading a large object to Swift, you can split it and upload it in parallel and get better throughput that way. Can you also download it that way? And the answer is yes, you certainly can, but it's not done for you like just through one API call. You can write a client that will easily do that. And I know that there are some clients out there that do that. I know. Yeah, Doug at Storage Made Easy has written stuff that does that, in fact. Yeah. Yeah, it's kind of some stuff that we're also looking at doing in Swift Client and things like that. It's good. Doug, you had a question.
So early in the talk, you talked about the new erasure coding for...
Global EC erasure coding, yes.
And when storage policies originally came out, they applied to the object layer.
Yes.
But the AC was still one policy. With this, are you able to do ACs per region or per...
The question is, do storage policies do apply to objects? And when they were developed, they did not apply to accounts or containers. Does the global erasure coding functionality enable a storage policy for the account and container storage? And the answer is no. Storage policies are limited to the objects, and the namespace there's one namespace, one storage policy per se for an account and for containers. Any more? In the back.
Yes, sir. With a global EC, do you get higher failure or ability to recover from more failures?
Accidentally, yes. Because one of the really great things about it is that since the fragments are wholly reconstructible inside of a single region, they are also able to use the remote region to recover as well. So you end up with a lot more. Now, you pay for that with the extra overhead, but yes, it is. You can get more durability.
Just when you were talking before about the small files,
Uh-huh.
what do you kind of consider small?
What do I consider small files when I was talking about small files? It depends, but it's definitely less than a megabyte, probably less than a kilobyte. Do you have anything on that, Rama? Is that roughly accurate?
Yeah, I would say when you have 50 million inodes on your device, you know there's a lot of small files.
When you have 50 million inodes on your device, you know they're small files. Was there another question over here? I think we have maybe time for one more.
I was going to follow up on that inode question. So what modern file system doesn't support 50 million inodes? Why is that a problem?
The problem is, via our testing, XFS is the best system for handling a large number of inodes or nearly full drives, as far as performance and able to cope with that. The problem is not the number of 50 million inodes per se. One of the problems is the fact that every single inode by default, for example, in 1604, Ubuntu 1604, XFS will be installed with a default 512 bytes. So if I'm storing a 1K file and I've got to create another inode for that, plus the D entries for the directory tree, and I have lots of those, you've got a 50% overhead just right there. And you're using up a huge amount of extra space. Unfortunately, that also goes into the page cache, which is the real pain point. Is Swift does a huge amount of directory traversals, and it does everything it can to keep all of that information in the page cache, but it does exhaust. There's more of that than there is RAM, and so we can't do it. So the slab file optimization, the small file optimization, will allow us to keep more stuff in memory, and therefore give more regular performance and higher performance, hopefully. So that's why. Great. Can I keep going, or am I out of time? Okay, we're done. Thank you very much for coming. If you have any questions, please feel free to ask. I'm fairly easy to find. Thanks for coming.